We're now going to look at the barotropic instability example, which is part of the linear wave problem set. So first thing, let's go again in the directory where we are working with the shallow water examples. Okay, and we're going to go in the MATLAB directory. So at this point, I'm going to generate the same grid that I've generated for all the others examples. So I'm going to run MATLAB. And I'm going to use the same script as we create initial grid. And in this case, I'm going to have this script so that it generates a flat grid with a 1/f plane. So this is going to be the same example as in chapter 10 that talks about the barotropic instability. So if I go towards the end of this, you can see that here I set the Coriolis parameter to a constant f0 and the topography to a constant h. So I'm going to save that, and I'm going to execute the script here, and this will create my grid in the input again. So here I have my my input grid, which is right here. Okay, so the next thing is to create an initial condition for the barotropic instability problem, which is a shear flow with a relative vorticity that changes sign in the middle of the domain. This is exactly as you'll have to read chapter 10 of the book, but this is a typical condition for which waves can go unstable. So I have the same configuration of the domain that we've been using so far. The initial condition, I'm going to change the name to of the initial condition, and in particular I want to make this a periodic flow at this point, as you will see shortly. I want to make it periodic in the east-west direction, and so I'm going to create an initial condition. Actually, I'm going to call it the same way, so that's good. So we go further on here, and so here there's a new section which is where we define the shear flow that will go unstable. And so here are some parameters. This parameter is L critical, L fast. These are the wave numbers of the critical wave numbers that will go unstable, and also the fastest wave number that will grow. And these are parameters that you can look up in the book and in the theory. And so here I'm going to create a shear flow U profile. Here you can see, and I'm just going to execute this script, and then I'm going to show you what this shear flow looks like. But the shear flow is only in the U component, the zonal component. And in addition to that, I'm also going to perturb this shear flow by adding a small perturbation epsilon. And this small perturbation epsilon is defined here in this TMP array, and it's going to be U0, which is the mean velocity of the shear flow, but in this case is about 1/4 of that. You can see here I use 1/4 of that. And then sine a wave, basically a wave perturbation. It has a wave number of L fast, which is the wave number of the fastest growing wave in the case of the instability. Okay, so I'm just going to execute this first by just typing this particular script. It would be important that you actually produce the initial condition using your own MATLAB, but if you're in trouble you can always use this one. And so now I created this this particular initial condition file, which is accessible by CTL, and we can look at what the U-bar initial condition looks like. If you do a p color of U-bar shading flat, in this case it looks like it's 0. Oh, and that's because, wait, we have to load the U-bar velocity. So we're going to load it using the load var command, CTL. Then it's going to be the first record, and it's going to be U-bar. So let's load that, and then let's plot it. Okay, so this is now the initial condition, and you can see that there's a mean flow here in the middle that goes from negative to positive, and then there, of course, there's a wave perturbation on top of that, which is 1/4 the strength of the flow. And you can see that here in this region here there's a strong gradient that goes from negative velocity to positive velocity. Now a better way to characterize the initial condition here is to look at the vorticity, and the vorticity in this case is just I'm going to call it vort. It's going to be u bar. It's a gradient in y of u bar. Okay, so let's compute that by saying 2 comma end minus, this is a very quick way to compute the vorticity, comma, and this is going to be 1 comma n minus 1, and then there's a minus sign in the u bar component of the vorticity. Because v is 0, the vorticity component associated with v is not here in this case, in this initial condition. Okay, so now we can plot the vorticity field, and we find that in the vorticity field there's a very clear negative vorticity in the middle of the domain, and then positive vorticity elsewhere. So we satisfy the condition for the vorticity change in sign in the domain, and you see it's a very narrow band. So this is our initial condition. At this point, we have to go and compile the model, in that we're going to change our configuration to allow for east-west periodic boundary condition. In other words, let me plot this again. The idea is that the waves, this initial vorticity patch is supposed to be going unstable, and then we're just going to allow this instability and these waves to propagate, around the east-west boundary condition. Okay, so we're going to do that by going in the ROMS model, and first let me log in on the master by typing X and putting the password. We're going to go into the ROMS SRC applications. Okay, so I've created here a new CPP def file that is called shallow 2D east-west periodic. So this is a copy of the shallow 2D that we use for the linear waves so far, but there are some changes that I've made. And in particular, the first change that I've made is I've reintroduced the advection terms, and that's because, as you know, part of the instability is associated with the fact that there's a mean flow that is advecting the wave, and so we have to keep this term in order to capture this type of dynamic. Now, because these instability can be numerically, let's say, challenging for the model, we're also going to introduce some viscosity, in particular the vis2, which is a Laplacian viscosity, or a del square u, if you like, and you can look the definition better in the README txt file that contains all the definitions. So we activate these two additional things, the advection terms and the viscosity. The rest remains the same, except that we are going to define the east-west periodic boundary conditions. Okay, so with this in mind, then we are going to create a new compile script that has basically is a copy of the script that we used before as shallow 2D compile. I'm just rename it, and I renamed it so that it uses a different CPP defs file. In this case, it uses the one that has east-west periodic boundary condition. I'm also renaming the executable file to be called differently, in this case shallow 2D east-west periodic ROMS, to characterize this from the previous executable, which was shallow 2D ROMS, which was without the advection and without the east-west periodic boundary condition. So having done that, I can just compile this script, and it should just run without any problem. And as this is running, I'm going to open another window here, and I'm going to log in on the cluster again, and I'm going to go and set up the example. So we go in shallow 2D, and in the input directory I've created a new .in file for the model, okay, which is the one east-west periodic, is a copy of this shallow 2D in, the one that we used so far, but I've made some changes. Now, to see what type of changes, the easiest thing to do is just to make a diff of these two. And if we do a diff, we find that there's a couple of changes. First, you can see that the viscosity 2D has been defined now to have a non-zero value of 600. This is in the new file now, in this file over here, the shallow periodic. We're also using a different number of records to do the averaging. This and average is instead of 360, 3,600, so it's a longer period. We're also writing the history file we're not really keeping track of the history file very much. In fact, it's only writing a record every 664,000 records, so really all we care in this case is the averaging, because we're interested in looking at the average solution. And also I'm running this example for longer, so now this n times here is 777,600 time, and that's because this instability takes some time to develop in this particular setup. Okay, so with this in mind, then the rest of the shallow2d.in file is the same. I'm just going to open it just to show you that it looks like any of the input files that we've been using so far. And so here, this is the file. The time step I'm using is still 240, which was we used for the linear waves, and all the rest is kind of the same. So with this in mind, then we can go now in the one directory above, in the shallow2d. This is where we typically run the model. Let's check if the model is finishing compiling. Yeah, it compiled fine. So we have the executable now. So we can go and check the executable is there. So all we need to do now is to run this model and generate the output file. And by now I'm not going to run the model for you because you have your model run script. So you just have to edit this, and you're going to have to change this particular one to have the right binary. So actually, let's do it together. So the binary file now is called shallow roms. So let's change that. Oops, sorry. vi run model. So the new executable file is going to be called like that. And then we have to also change the .in file, which is going to be called this one over here. And so we can change the .in file here. Okay, so at this point we've configured our PBS, or run script. So all we need to do then is to run this q sub f12. Okay, we do qstat, and you can see that the model is running. Okay, so I've ran this. It's going to take some time to run, and I've created in the output directory is going to create some averages file and so forth. I already renamed these for this particular lfast. So this is the output file associated with the case that we're running right now. And so we're going to go and plot this file. So we go back into the MATLAB directory, which is in the Neo GFD root ROMs example and so forth. There was a okay, so that's the directory. So there's a script here called plot barotropic instability. Okay, and this script basically reads the two averages file. I have two examples here that I ran. One uses initial perturbation that is associated with the critical wave number, and another one is associated with initial perturbation, uses the fastest growing wave as the initial perturbation. And the one that I'm going to show you now is the one associated with lfast, but you can run both examples, and in fact in your initial condition file you can see that if you go and look, where the perturbation is executed, you will find that there are in fact two examples here. One that uses lfast, which is over here, which is the one that I actually used, and the previous one, which is commented out, which uses this other parameter, which turns to be L critical. Okay, so having said that, let's plot our solution, and what we're going to plot here is the relative vorticity. I'm going to create a figure first, and the idea is that the relative vorticity is easier to see in the relative vorticity field, the structure or the sign of the barotropic instability. So I'm just going to start plotting this. Let me select that. Okay, let's look at the figure here. Okay, so this is the initial relative vorticity, which is negative, and we're day 45 here. And you see that as time is progressing, you start seeing that this initial vorticity field is being perturbed. In other words, the mean flow is being perturbed, and you start generating these vortices, which are associated with the barotropic instability. And you find that eventually these vortices are starting to coalesce with each other, merge as they entrain each other. And so beginning from an initial relative vorticity field, which was a nice mean, you end up having these vortices which become kind of large scale, and you can see now there's only 2 of them, and in the periodic boundary condition, and they have entrained fully themselves, and eventually they will entrain each other again. So this is the example of the barotropic instability, and with this I'm going to close this tutorial. Thank you.